talk is on curve shortening flow. So this is like a big subject. It's a part of mean curvature flow. Mean curvature flow is the high dimensional equivalent. So in this like 1 hour, I'll just try to give.
Theodora, we can't hear you. If you try muting and unmuting your microphone, that might fix it.
Okay, what about now? The people say they can hear.
Okay, we can all hear you. Sorry, Theodora, my mistake.
Is it good? All right.
Go ahead.
Right, so we're going to give a small introduction on curve shortening flow. I'll try to motivate the definition and give you some cool things that you could do with curve shortening flow. So these are one-dimensional equations. So let me start by introducing let me start by introducing curves in the plane. Okay, so can you see the cursor as well? Okay, so here's like a curve, gamma, capital gamma on the plane. We're gonna use a parameterization. We write it as little gamma. So little gamma is a parameterization of a curve. It goes from an interval of R to R2. So this way I can write my gamma as the components X and Y that I write as gamma 1 and gamma 2. So this is a parameterization of my curve gamma. And we're gonna call this parameterization an immersion as long as the derivative has length never always positive. Okay. We would also call the immersion an embedding if we have no self-intersections. So something like a figure 8 has a self-intersection, so this is not an embedding. And from now on, we're going to assume that our curves are embedded, immersed, and embedded in particular. So for notation, capital T will be the tangent vector to our curve at gamma u. And this tangent vector, we can compute it as a derivative of gamma at u over the length of the derivative. Okay, so this is like a unit tangent vector. And depending on how we parameterize the curve, like in this picture, we parameterize it going this way. The direction of t will give us the way we parameterize our curve. Now, if I take this unit tangent vector t and I rotate it by 90 degrees clockwise, I'm getting another vector that I'm going to call n, and this is the unit normal to my curve at gamma u. Now, having a parameterization, I can compute the length between 2 points A and P by integrating the length of the derivative. So this gamma prime u du is what we call the infinitesimal arc length. So what exactly is arc length? It happens that there's a special parameterization that I will denote by S, where the derivative has always length 1. In this case, if we parameterize the curve like this, then we say that the curve is parameterized by arc length. And you can see in this case, our S would move from 0 to the length of gamma. Now, what's the curvature? So the curvature of a curve is a way to measure how fast the normal to the curve turns. And this curvature, this quantity has a sign that indicates if we're turning left or right. So for example, in this picture here, we're going this way. And every time I turn right, the curvature is negative. Every time I turn left, the curvature is positive. And depending on how much I'm turning, changes the length of the curvature, the argument of the curvature. And how can you compute this? This you can compute by taking the derivative of the normal. So the curvature is given by taking the derivative of the normal and dotting with the tangent vector. So dotting with the tangent vector is not any restriction, because if you can note that the normal has length 1, so if I dot with itself, I get 1. So if I apply the product rule, you see that d nu ds has no normal component. Okay, so here nu is a vector, so when I'm talking about the derivative of a vector, I'm talking about that component-wise. Okay, so this guy here is a vector who is parallel to the tangent vector. Similarly, we can play the same game with the tangent vector, and when you take a derivative, then you get, again, the curvature, but now it's a vector that is parallel to the normal. So let's see an example. So take the curve gamma from 0 to 2 pi, this should be R2, okay, it's a typo here. So you take this curve given by theta goes to R cosine theta, R sine theta. So we all know that this is a curve that, this parameterization describes a curve which is a circle of radius R. So if I compute the tangent vector here, I take gamma prime at theta. This will give me minus R sine theta, R cosine theta. And I divide by the length, which is R, so I just get this vector. And if I rotate it again 90 degrees clockwise, I get the normal, which is cosine theta, sine theta. Right, so remember S denotes the arc length, and we said ds d theta is the length of the derivative, which gives me exactly R. So now we can go and compute the curvature of this simple example. Remember, kappa is given by d nu ds dot t, okay, by this formula up here. And I can do the chain rule here to get d nu d theta times d theta ds. This is this guy, and dotted with t. And I just use ds d theta here, what I got, okay? And this guy here, we can compute directly from this formula for nu. Okay, and it actually gives me exactly t. So this d nu d theta dot with t gives me 1, d theta ds is 1 over r, and this is a simple proof why the curvature of a circle is exactly 1 over its radius. Right, now note that this is like this parameterization has something like really special. So if you look at theta goes to gamma theta, this is r cosine theta, r sine theta, but theta is something special for this vector. It is actually the angle between the position and the x-axis. And you'll see why, now in the next slide, why this is a nice parameterization. So this is actually called parameterization by turning angle. And let me repeat, in this parameterization, theta gives me a point gamma theta, which is such that the normal there makes an angle theta with the x-axis. Okay, so I go to the point gamma theta, this is the normal, this is the x-axis, and the angle between the theta. All right, so this is not parameterization by arc length. So when I compute the tangent vector, to make it unit, I need to divide by the length of gamma prime theta, because it's not necessarily 1. However, parameterization is nice because we know no matter what that the normal is cosine theta sine theta. Now, unfortunately, we cannot do this always. We can only do it if for each theta there is a unique gamma theta. For example, this is always possible for convex curves because there are no 2 points that have the same norm. All right. Moreover, then when we use this parameterization, we can compute d nu ds. Right? Remember, this is what gives me the curvature. So this is curvature times tangent vector. And if you again apply the chain rule, you find that d theta ds is equal to the curvature. Okay, so this is another way, if you have this parameterization, to get the curvature. And this formula, it also gives you this very nice property. So if you integrate this, now S is like arc length, so you integrate between 2 points, the curvature, change your variable from S back to theta, and this is equal to this is pretty much like the difference of the normal at the endpoint. And if you have a simple closed curve, you do the same here, you're going to get 2 pi, you get that the integral of kappa is always 2 pi. So this is true for any simple closed curve. All right. Okay, so, and please interrupt me if you have any questions, okay? It's difficult to see if everybody's following. So if you have no questions on curves on the plane, we can move on to define curve shortening flow. All right, so now before we had just a curve, now we're gonna have a family of curves. So this is my family of curves. And we will say that this family satisfies curve shortening flow if it moves in a specific way. So I'm gonna use again a parameterization. Before we just had parameterization of one curve, so we had little gamma going from capital gamma to R2. Now this I indicates the different gamma t's. Okay, so I'm gonna have a parameterization of the family, and I want the family to move according to this rule. So I want my d gamma dt to be equal to minus kappa times nu. Okay, so I'm using little nu now for the normal. This is what before it was capital N. So we want the curves to move in the normal, along their normal, and with speed equal to their curvature. All right. Now, if you look at this equation, and remember first slide, we had that dt ds, t was the tangent vector, is equal to minus kappa dot nu. Okay, this is how we get the curvature. The curvature is given by how the normal changes, or the tangent vector. Okay, so this we had from the definition of the curvature. And this capital T is the tangent vector, so it's gamma s. So this is plus gamma ss. This equation tells me that the left-hand side is equal to the derivative of gamma with respect to t. So curve shortening flow becomes this equation. Okay, so I'm putting it in quotes because it's not exactly that. S changes in time, but morally, the equation is gamma t equals gamma ss. And this is now a heat-type equation. So a heat-type equation is an equation that says d dt equals the Laplacian of the function. In one dimension, the Laplacian of the function is a second derivative. Okay? In general, say in two dimensions, it would be fxx plus fyy. Okay? But it just one dimension is df dt equals second derivative of f. Now, this is a very well-known equation. This is an equation that describes how distribution of heat changes in time. Okay, so it's very well studied. So we can actually use techniques from the heat equation and try to apply it in curve shortening flow. Now, before I say more about this, let me just make an example here. What happens at circle? So let's try to find a solution to the curve shortening flow starting from a circle of radius r0. Okay, so I have my gamma theta here that I'm going to write as gamma theta comma 0, and 0 here to indicate that this will be my initial curve. And this is given, this is a circle of radius r0. Okay, so as I said before, this is r0 cosine theta times comma sine theta. So we're trying to find a solution for curve shortening flow starting from this curve. A good guess would be to try to preserve the symmetries. So here I have a curve which is rotation symmetric, that's the circle. So I will try to find a family of curves which is also rotationally symmetric, in particular circles. So I'm looking for a solution of the form gamma theta t equals rt cosine theta sine theta. Okay, so this is a very good guess because in general, when you have an equation, you will need to preserve the symmetries. Okay, and particularly with curve shortening flow, in general with mean curvature flow, a lot of symmetries are preserved. So let's try to do this. So you put this guess solution, and you want to determine r. Right. So you go and you plug this back to your equation. D gamma dt, this changes only the radius. Okay, so you get r prime of t, cosine theta sine theta, and kappa dot nu is kappa is 1 over the radius, and my normal is cosine theta sine theta. So if you want the speed to be equal to minus kappa nu, then you get this simple ODE. Okay, so r prime equals minus 1 over r. You solve the ODE by integrating, okay, and compute, and you get that the radius at time t0 is equal to square root initial radius squared minus 2t0. Okay. So this shows that, yeah, there does exist a solution. It will stay circular, and it will just shrink. And this formula here tells me that something has to happen when t0 is r0 squared over 2. So what happens is that you start with a circle, you flow by curve shortening flow, your circle is going to start shrinking until it finally disappears to a point at time r0 squared over 2. Okay, now why do we choose to use this equation? So curve shortening flow is a flow that moves the curve so that it reduces its length as fast as possible. So, like often, like in variational problems or in nature, what we want to do is we want to minimize some energy. So this way, this is like a parabolic way of doing this. And of course, we want to do it like in the fastest way. So here, the energy is the length. And what you want to do is you want to take something and move it so that it reduces the length as fast as possible. So and there's like it's not difficult to see why curve shortening flow is the best, the best you can put so that this happens. So let's see this. So again, let's just take a curve. Now let's parameterize by arc length. This we do it usually to make the computations easier. So my curve gamma goes from A to B, an interval to R2, parameterized by arc length. And what we're going to do is we're going to vary gamma. So you vary gamma. Now gamma t here is just a parameter. So I'm changing gamma a little bit to its normal direction by the function. So take any function f, and you change your gamma along the normal direction. How much? By t times f. And t is going to move from 0 to epsilon. When t is equal to 0, you get back your original curve gamma. When as t grows, this distortion gamma t moves away from your original gamma, but to an epsilon neighborhood. Right. So we want to see what is the best, how can I vary here f? What is the best f I can do? So my d dt, the way that the length changes the time t equals 0, is the largest. Okay, so it's going to be negative, so it's the smallest. Okay, so let's compute the length of gamma t. Remember, when I compute the length, I just take integral from a to b gamma prime t. And when I compute this gamma prime t, I'm just like taking the derivative of this guy, the derivative with respect to s. So you get gamma prime minus tf prime nu minus tf nu prime. Now we have to remember our the equation from the first slide. Nu prime gives me the curvature. Gamma prime is the tangent vector. Okay, so these are tangent vectors, these two, and this one is normal vector. So you can compute this. You only get the norms of the two. Okay, because nu dot t is 0. You get this integral. So now when we compute like the derivative of the length at time t equals 0, you get exactly minus curvature times f. And now you can use either Holder or you can use Cauchy-Schwarz. Either gives you you have an inequality, and the equality happens only if your f is a multiple of kappa. Of course, this is under some normalization, right? So you assume that your speed is integral of f squared 1, okay? Because of course you can make f infinite and then like, that doesn't make sense. So we have some normalization, for example, like integral of f squared equals 1. And under this normalization, we conclude that the best way to move so that the length decreases as fast as possible is along the curvature. All right, so this is this shows that this is a good flow to use if you want to minimize energy such as length, and in higher dimension, of course, length will be replaced by area. All right, so let's go back to the fact that the heat equation, that the curve shortening flow is a heat type equation. And let's see what we can use from the heat equation to curve shortening flow. So remember, heat equation is the equation df dt equals fxx, or in higher dimensions, the right-hand side will be the Laplacian of f, which is the sum of fxi xi, and curve shortening, which is the motion of a curve by its curvature. So looking at the heat equation, and let's look at the initial value problem. What is the initial value problem? Is the problem of trying to find a solution to the heat equation starting from a particular function. So in general, if you put any smooth function, you can have a solution of the heat equation that starts by this function. Now, if you look at this equation, here on the right-hand side, I have two derivatives. So you think that it only makes sense for functions that are at least C2, or at least like twice differentiable. However, you can show that the heat equation has indeed a solution starting from any bounded continuous initial data. There, you do not need C2, but what you can show is that when you solve this equation, this will be C2 up to the open times 0. Okay, so at the beginning it's not, but immediately for any time positive, it becomes smooth. And you can show that this solution converges in C0 to your original bounded continuous initial data, okay? Which is a very nice property, because it says you do not have to have smoothness conditions on your initial data to start the flow. Now, turns out that the same thing happens for curve shortening flow. Well, not the same, but something similar. So again here, because you have the curvature on the right-hand side, and remember the curvature is pretty much the derivative of the normal, okay? So it requires two derivatives of your gamma. So this makes sense when gamma is at least twice differentiable. However, when you're looking at the initial value problem, so what kind of curves can I start with? It turns out that you can start with any convex curve. So any convex curve, you allow corners, it doesn't matter, and you run curve shortening flow. This flow make it immediately smooth and strictly convex. Okay. Again, what do we mean with a solution here? We mean something that's gonna be smooth up to the open T0, and it converges in like Hausdorff distance or C0 topology to your original convex curve. Okay, so this is very useful because it allows you to start with any convex initial data. Sorry, somebody raised their hand.
Yeah, so if you want to answer that question,
yeah. What's the question?
You can lower their hand. Emmanuel, did you want to ask a question real quick?
Yeah, so we're still working, the X is still in R, it's still one dimensional.
I couldn't hear.
So
could you repeat?
So X is still in R, we're still working in one dimension, correct? No? Or
Yes.
just- Okay. I just
Yes.
wanted to be sure. Okay, no problem.
Yes, yes, yes. We're still working in one dimension, but just to make things simple. Many of these things that work in higher dimensions as well. It's just harder to define things.
Okay, no problem.
Mm? Mm. Okay, so another very useful property that originates again with the heat equation is the maximum principle. So what does the maximum principle say? So you start, say you have a solution F of your heat equation here. Define it omega. This is, again, so in one dimension, this would just be an interval of R cross 0A. Okay, so here's my domain. This is space, omega, and the time goes from 0 to A. Maximum principle says that the maximum of F occurs at what we call the parabolic boundary, which is this, and this. Okay, this is what I write here. So the maximum of F will occur either at the initial data, which is this part here, or at the boundary cylinder, which is this part here. Right, and this maximum principle is pretty much what we do in school, the second derivative test. Okay? Because what you do is, let's, without loss of generality, let's assume that this guy here, this maximum is equal to 0, okay, or like something like less than 0. I can always do this by translating my function. And assume that somewhere in the interior, you get a point where you actually get F bigger than the right-hand side, which we said, okay, let's assume it's 0. And let's take the first time that this happens, okay? Since back here, your function is negative, and here it just becomes positive, so the derivative with respect to t, it must be bigger or equal than 0. So df dt at this point is bigger or equal than 0. Also, we can choose this point on this on the time slice here, so that it is the maximum, and therefore fxx is less or equal than 0. This implies that df dt minus fxx is bigger or equal than 0, but the equation gives me that it's equal to 0. Of course, as it is, it's not a contradiction immediately because we get 0 bigger or equal than 0, but this is a standard thing that happens when you try to apply maximum principle, and usually when you reach this point with 0 bigger or equal than 0, then you can tamper a tiny little bit with your function to get a strict inequality. And the way you do it here, for example, is by changing f to f plus epsilon t. So you add a little bit that will make the equation, that will make the inequality strict. Anyway, but the idea is just go to the first maximum and apply the second derivative test. Okay, so let's see how we can use this to curve shortening flow. So the first application of this maximum principle to curve shortening flow is what is known as the avoidance principle. So the avoidance principle says the following. So if you have two curves, which initially are disjoint, let's call them like gamma 0 and gamma 0 tilde, so they're intersect empty. And let's say here are their flows, gamma t and gamma tilde t. Then if they are initially have empty intersection, then at any time slice, the same will still hold. Okay, so if you start by two curves that are disjoint, then they cannot intersect later on. And again, so here's like the sketch of the proof. You start by two curves that do not intersect. Start running curve shortening flow. And let's assume that at some point, and let's choose the first time, that their intersection is not empty. Since it's the first time, there must be a point where the two are tangent. Okay, so here's my gamma t, and inside this gamma tilde t. So they're tangent, they have the same normal at that point. And because you see gamma tilde lies inside gamma, it curves a lot more. Okay, so the curvature of gamma tilde at this point is bigger than the curvature of gamma at the same point. So, which I denote by kappa tilde and kappa. So kappa tilde bigger than kappa. This means that at that time, gamma tilde moves faster than gamma. So just a moment before, they must have been intersecting. Okay? And this contradicts the fact that we chose t to be the first time. And again, like this is like, if one were a rigorous proof, it's a little bit more complicated, but this is the idea. Okay, so this is like this what I call just a sketch of the proof. Right. Now, another thing we can do with this curve shortening flow, sorry, with the maximum principle, is that it helps us show that a lot of quantities are preserved. For example, a nice property is that convexity is preserved. A curve is convex if whenever I connect 2 points on the curve, this segment lies inside the curve. And looking at the curvature for embedded curves, this means that kappa is positive. Okay, so it's equivalent to saying kappa is positive. So if I take kappa positive, I can use maximum principle to say that kappa remains positive. Now, how can we do this? We gave the definition of curve shortening flow as a curve moving by d gamma dt equals to minus kappa times mu. Now, using this equation, you can write evolution equations for a lot of geometric quantities of the curve. For example, you can write how the curvature evolves. And it turns out that the curvature evolves under this equation. So the derivative of the curvature equals to kappa SS plus kappa Q. If you forget about this term, again, this looks like a heat equation. Well, this is exactly a heat equation, but it has this additive term. Now, this additional term is actually like helps because it's positive. So here, again, like how can we prove that kappa is positive? So let's assume we have this at the beginning. So let's, for simplicity, let's take a compact curve. So we can say that kappa is bigger than epsilon on the initial surface. And we're going to show that kappa is indeed also bigger than epsilon for all times afterwards. So assume not, and take the first time where kappa is equal to epsilon at some point p. And then at this point pt, by the same reasoning as before, kappa t must be less or equal than 0, and choose it so there we have the minimum for the specific time slice. So kappa ss, the second derivative, is bigger than 0. So kappa t minus kappa ss is less or equal than 0. But this equation tells me that it's also equal to kappa cubed, which at that point is equal to epsilon. Okay, so we get that epsilon cubed less or equal than 0, contradiction. Okay, now remember the avoidance principle says that if I start with two curves that are originally disjoint, then they will stay disjoint. So let's take any simple closed curve, here gamma 0. Okay, and we can put a circle around it. We've seen at the beginning how the circle evolves under curve shortening flow. And we saw that the circle stays a circle and it will disappear at a point in finite time. Okay, and since these two guys are always disjoint, this means that this curve gamma 0 cannot live forever under curve shortening flow. You cannot, something should happen to this curve before the circle disappears. Okay, what can happen to the curve? Either it also disappears at a point, or another problem is that maybe at some point the curvature goes to infinity. So remember the equation for curve shortening flow is the speed equals to the curvature. So this equation only makes sense as long as the curvature is bounded. If the curvature goes to infinity, then we cannot, with what we know so far, in introduction, we cannot continue the flow. So this means that any, just the avoidance principle tells me that any simple closed curve will either have a curvature blow up or it will disappear at a point in finite time. So disappearing at a point, it also means that the curvature blows up, but it's not. So when the curvature blows up, we call this that a singularity is forming, and this particular singularity, everything extinguishes at a point, is not. It's a very good singularity because we know exactly what happens. All right, so here's like, of course, I'm not gonna prove this, but this is like an amazing theorem. Then it says that actually any simple closed curve will contract to a round point. So this was proven first by Gage and Hamilton in case your curve is convex, and later Grayson showed that take any simple closed curve, this curve will become convex in finite time, and it will then, by Gage Hamilton, contract to a round point. Okay, so actually there is like this nice video which now I know how to show you. So let me just show you a couple of examples. Okay, so these are some examples of what happens to curves under curve shortening flow. Let's see this one. Okay, so this is an example of a spiraling curve, and now under curve shortening flow, it starts unraveling, but the curvature is always bounded, so the flow exists and is smooth. Okay, and it will keep unwrapping. It's also amazing that the rate that the enclosed area changes is always constant in time. So it keeps unwrapping. Okay, and now it's almost unwrapped. It will become convex, and now it disappeared at a finite point. Okay, oops. How do I go back?
Best of jazz, best of jazz.
Okay. Okay. Sorry. Okay. Okay, and this you can do. In fact, with any, you can draw any curve, and there are ways. You can do it online. You can draw any curve, and then you get like a solution to the curve shortening flow, and you can see that anything like always unravels to a round point. Okay, so now let me move on and talk about ancient solutions. So ancient solutions are solutions that are defined for all times in the past. So the interval where t is defined goes from minus infinity up to some time. This time could be also plus infinity. Now, with both the heat equation and the curve shortening flow, these are both equations that are well posed forwards in time, meaning that if you give me initial data, I can define the flow for at least a short time, but only forward in time. Moreover, if the solution lasts forever, so if you can let t go to plus infinity, then your solution tends to an equilibrium. What do I mean by an equilibrium? Say for the heat equation, which was d f dt equals Laplace. Again, like in one dimension, this is the second derivative. So if you have a solution that lasts forever, you expect that as t goes to infinity, your solution will tend to a solution of this equation. Okay, so just the right-hand side. You forget about t, the t part, and just the right-hand side being 0. Same thing with curve shortening flow. You expect that if you have a solution that lasts for all time, as t goes to plus infinity, your curve should converge to something where the curvature is equal to 0. Pretty much here, curvature equal to 0 in one dimension. What is it? It's just a line. All right, so this indicates that we should not expect to be able to find many solutions defined on a large backward interval. Okay, because the more the solution has lived, the more time it had to short itself out. So this gives hope to classify ancient solutions. Okay, and we're not just studying ancient solutions because of this reason, because they seem to be easier to classify. We study ancient solutions because they are fundamental objects in understanding the flows. So as I said before, not just, so curve shortening flow is just like a simple example, one-dimensional example, but a lot of geometric flows have this problem that the flow stops and cannot, you have an issue when the curvature or its right-hand side, the speed goes to infinity. Okay, so here we have an issue when the curvature goes to infinity. And what we want to do is we want to study these high curvature regions to be able to flow past the singularity. And it turns out that these singularities, if you zoom in, what you get is an ancient solution. So these ancient solutions, they pretty much model singularities of curvature flows, or in this talk of curve shortening flow. Okay, so what can we say about ancient solutions? So for the heat equation, it is known, there's a theorem of suppléance, that if you have an ancient solution with specific decay at infinity, then U has to be constant. Now the decay at infinity is, so little o means that what I have here goes to 0 as x plus square root of t goes to infinity. So if your solution has this decay, then it has to be a constant. Or we can have like less restrictive decay if we assume that U is positive. So this is for the heat equation, and this is a similar theorem as Liouville's theorem for harmonic functions. So this theorem says that if you have a solution to a harmonic function, which in one dimension is second derivative equals 0, and U is bounded above or below, then U has to be constant. Of course, like now in R, this is a very simple thing to do, because once you know that the second derivative is 0, you know your function is linear. So of course it cannot be bounded unless it's constant. Okay, but in higher dimensions, it's more interesting. Okay, and we can classify ancient solution under some conditions in curve shortening flow. Here, unfortunately, we cannot classify all solutions. We have to add some kind of geometric assumption. And the ones we're gonna add is, well, we're gonna keep embeddedness. We said at the beginning, we're just like looking at the embedded example, and we're gonna add convexity. So we're only gonna look at convex ancient solutions. Okay. So doing this, there are only 4 different solutions. There is a shrinking circle. There is the angular oval. These are both compact examples. I'm going to explain what this is. And if you add the non-compact case, you have the straight line, and you have a solution called the Grim Reaper, okay, which I'll also define. So this was a theorem of the Scalabulus, Hamilton, and Sesson in the compact case. And recently, with Langford and Tinaya, we gave a new proof of this compact case that actually extends to the non-compact case as well. Okay, so let me just show you what these solutions look like in the last slides. Okay, so I'm saying these 2 non-compact examples, they also happen to be what are known as translating solutions. So here's the definition of translating solution. We say that the family of our curves is a translating solution if all the slices are translations of the slice 0. Okay, so I have my slice 0, I translate it along some direction E, and I get my slice T. Okay, so this, as you can tell, are very, very special solutions. So here, by this equation, I can see that d gamma dt, which is kappa times n by the curve shortening flow, should be equal to E times n. Okay, because here d gamma dt just gives me the vector E, and I'm just dotting afterwards with n, the norm. So this gives me that the curvature has to be equal to minus E dot n on gamma 0. So these translating solutions, even though it's a parabolic equation at the beginning, so it has the time in it, it pretty much boils down to an elliptic problem. So just find a curve that satisfies this, and then when you translate it, you get a translating solution to curve shortening flow. Okay. So to start computing something, let's set E to be E2. We are in R2, so that along the y-axis, and we stick with convex functions. So because my curve is convex, kappa has to be positive. If kappa is positive, E2 dot n has a sign, and therefore my curve is a graph. So you write down what the equation looks like for a graph, and it's not difficult to see that you get only 2 convex translating solutions. You have the straight line, okay, that this would be a vertical line. So here for my line, nu or n, dot E2 is 0, and the curvature is 0. So this equation is satisfied. And a more interesting example is the Grim Reaper. So the Grim Reaper is the graph of the function x goes to minus log cosine x. Okay, and again, it's a simple exercise. We can compute the tangent vector. This is cosine x sine x. The normal vector, sine x minus cosine x. And we can compute the curvature. And the curvature turns out to be cosine x, which is minus n dot E2. Okay, so once you write down this graph, it's not difficult to show that this is indeed a solution to this equation, kappa equals minus E2 dot n. So therefore, the Grim Reaper is a solution to curve shortening flow that moves by translation. And this function here, minus log cosine x, is a function that is defined only between minus pi over 2 and pi over 2. And it looks like this, and it's asymptotic to 2 parallel lines of width pi. Okay. Now, for the compact ancient solutions, we have there's a shrinking circle. Before, when we computed how the radius changes, so I start by a circle and I want to flow it by curve shortening flow, we computed how it changes. Now, by using this equation, I can write an ancient solution. So take a circle here of radius RT. T will run from minus infinity to 0. And I set my RT to be square root of minus 2t. Okay. You see, as t goes to minus infinity, this goes to infinity. So I get circles of larger radius. And when t goes to 0, I get a point. And when you compute minus r prime t, this gives you 1 over square root of minus 2t, which is the curvature of the circle of radius rt. Okay, so this family satisfies curve shortening flow. Right, now we said there's one more example. This is the unguided oval. So the unguided oval looks like this. I'm going to show you a video in a second. So the unguided oval looks like 2 Grim Reapers joined together. it has an equation. So this is the equation. So AT, this is the t slice of the angular oval, satisfies this. Cosine x equals e to the t hyperbolic cosine y. Okay, but this is just an equation. You can show that this satisfies curve shortening flow. But the important thing is to understand the picture. So the picture looks like as t goes to minus infinity, these tips here, they converge to grim reapers. And in the middle, I see two parallel lines. If you compute the curvature of this guy, you get something that is very close to cosine x. So it's cosine x plus exponentially small in t as t goes to minus infinity. Okay? And remember, kappa equals cosine x is the curvature of the grim reaper. So this is why this converges to the grim reaper. So let me show you just quickly this. Okay. Okay, so this is an illustration of how the angular oval, again, as you go back to minus infinity, it looks like two grim reapers, and as you approach zero, it looks more and more like a circle. Okay, and right, so my time is running up. And let me just quickly say that one can do the similar things in higher dimensions, but of course, like things become much, much harder. An important thing is there's a theorem of Xuzhou Wang that, again, like here we're looking at ancient solutions, okay? But in mean curvature flow, higher dimensions is not curve shortening flow, it's mean curvature flow. We're looking at surfaces or hypersurfaces that are evolved by their mean curvature. Again, this is a quantity that tells you how the normal changes. Okay, so right. So for mean curvature flow, again, we can look at ancient solutions. They have the same importance. They tell us how singularities look like, and by this very nice theorem of Xuzhou Wang, ancient convex solutions, they are in two categories. There are the ovaloids, which are solutions that sweep up the whole space, and there are pancakes, which are solutions that line a slab. So always your solution, when you take the union of all t's, either you will cover the whole space, or you always confine between two parallel hyperplanes. And now there's like a big interest in classifying these solutions. Now, for the ovaloids are well more understood than pancakes at the moment, because it is known, this is a theorem of angular Daskalopoulos and Sesson, that there exists a unique rotation symmetric ovaloid. And moreover, they actually, like very recently, they changed this rotation symmetric to something far, far more general, which is, well, I don't want to get into it, but non-collapsing and two convex. Okay. Now, for the pancakes, along with Langford and Tinaglia, we've showed that in the rotation symmetric case, there exists again a unique one. Okay, so let me, I want to show you these pictures of how these objects look like. Okay. Right, so here's the rotational symmetric, whoops. Okay, yeah, this. So this is the rotation symmetric ovaloid. So this guy in the middle, it looks like, as t goes to minus infinity, like a cylinder, whereas at the tips, it looks like paraboloids. And as t goes to minus infinity, this becomes more and bigger, and it will fill up all the space. For the now for the pancake, okay, the pancake looks like this. Actually, this is also the flow as well. Okay, so it's always between two parallel hyperplanes, or let's say planes, like just 2 dimensions. And at the edges, it looks more and more like a grim plane cross arc. Okay, and this solution here looks very much like a rotated ungular oval. So the ungular oval was the one-dimensional example that we saw. Okay, and let's oops, sorry, where were we? Okay, right, and so these are the examples that we know, and actually we are working into constructing now new families of these pancakes without any specific symmetries. Okay, I think I'll stop here. Thank you.
Thank you so much. Does anyone have any questions? Ode, I saw your hand first. Go ahead.
Oh, I have to.
Hi. Thank you for the very good presentation in slide number 7. So you mentioned that the curvature is the derivative of the norm or the normal vector, just to double check.
Wait, you said
Slide 7. The curvature is the derivative of the norm. The t equals like the very top on the right. You mentioned that it's the derivative of the norm or normal cone. Sorry, normal vector.
So kappa is the derivative of the normal vector of this mu.
Okay. All right. Thank you.
So there is another question about the embedding. Do this in any way have a relation to someone embedded in some high dimension? So there's a question here about the Sobolev embedding. Not a connection that I know.
Yeah, Patty, go ahead.
Hi.
And then we'll take Caleb's question after Patty.
Thanks for the talk. I just wanted to know, if there's like any. So you're saying in higher dimensions, there's no with the mean curvature flow. You don't know. You have not classified all ancient solutions, right?
No.
Okay. Do you have any idea if there's like a finite amount of like, I don't know, like, do you have any conjecture in that aspect of like, I think I don't know.
So, right. So say for these ovaloids in dimension 2, it is known that it's only one. There exists only one. And it is rotation symmetric. Now, for the pancakes, well, we actually are working now in classifying them in terms of what we call the squash down, is how they look back at infinity. So for example, like this pancake, this rotation symmetric pancake has a squash down. Think of, you bring everything to 0 as you go to minus infinity. But what you're gonna see is a circle. So the slab will disappear, and what you see is just a circle. Okay? So we try to classify them in terms of what you see at minus infinity. But say for the circle, we believe there's like infinitely many solutions that will give you the same squash down, and they're all ancient. So for the pancakes, we can construct infinitely many, so they're not a finite amount. And we believe that maybe you can classify them as families, but not, they're not gonna be 1, 2, 3. You know what I mean? Makes sense?
Right, but like I'm saying, like you think that there's a finite amount of families, I guess. Like things like, they're all gonna look like, there's not gonna be any like very weird one. I don't know. Thing.
No, it's not gonna be finite because and this, as I said, is very recent, so we're still working on this. But we can definitely, like this pancake, which is rotation symmetric, we can construct solutions that have symmetries of any polygon. So for any polygon, we can construct a solution.
Okay.
So already, these are like infinitely many.
Mm-hmm. Thank you.
Yeah. Oh, and there was some.
All right, so Caleb had a question on, out of curiosity, do you know why it's called the Grim Reaper curve?
Okay, so there is this, that's interesting. So, there are many, I don't know for sure, but here's the most common thing that I've heard. So we talked about the avoidance principle, when you have two solutions, and that are disjoint, then they have to stay disjoint. Now the Grim Reaper is a curve, let's put it like this, right? And it moves with speed 1. Okay, so it moves like this. So, and they say that at its pass, it kills whatever it finds. Okay, because anything that is here must disappear when the Grim Reaper passes. So because it kills everything on its way, it's called the Grim Reaper. I hope that makes sense. Right.
Does that answer your question, Caleb?
Yeah. Yeah, exactly. Look at it and you cannot see why. Some people say that it also looks like what's the name of this? Like seeds? The thing that the Grim Reaper holds? Which is like a curve. Yeah, that one. Yeah. Exactly. But I think it's more.
All right, any other questions?
All right.
All right, if not, let's thank our speaker one more time. Thank you so much, Theodora.
Thank you. Yeah, great. Thanks for listening.